This tutorial was prepared by a different team of folks. The lead was Lindsey, who unfortunately had an issue because of the changes in immigration orders and whatnot, and she had to basically take an emergency trip today to deal with that. And so I'm kind of replacing her, but we have a team of co-instructors as well. So in order to, we're going to repeat the same process. You should grab these materials. In this case, the materials are in the intro Jupyter tutorial. You can clone it with that command, just like we did before. If you had already done that, remember now in the intro Jupyter directory, type git pull, and you should get that content in the same manner. And this is going to be the same thing that we'll be doing over and over for all tutorials. I'm going to give like a 2-minute intro to what are IPython and Jupyter, for those of you who may not know exactly where this came from. IPython began its life as that single, very small 250-line script that I told my advisor when I was a PhD student in particle physics would be just an afternoon of procrastination, and 20 years later, it has kind of consumed my life. So that's how terrible I am at time estimation. IPython was designed originally as a command line tool to do interactive computing, meaning type a little bit of code, see the data, plot it, and iterate on that, which is the workflow that is very natural to scientific computing. This is why MATLAB, IBL, Mathematica, Maple, virtually every scientific computing environment has a good interactive component to it, which is less common in industry software engineering. In fact, in the Python community, the sort of software engineering side of the Python community tends to use these tools a lot less. The scientific community tends to use them a lot because iterating against your data, looking at it and typing code that isn't associated with a preset set of requirements, but rather is your own exploratory process, is kind of the norm, more the norm than the exception in science. And IPython was born for that. IPython uses Python, and every Python code you can type, but it also has some extras that you will learn more about later today. I want to flag, though, that everything you're seeing today is the result of a huge scientific community that has contributed. I got interested in this because I thought it was fun. I was a grad student procrastinating, but all of the vast amounts of machinery that exist today in Python are the work of a very large team, and I barely do any of that anymore. And I want to make sure that I credit both the people who work close to full-time on the project or who have spent a lot of time on it, and a very long tail of open source contributors. And that's some of the spirit that we want to convey with this workshop, is that these projects and these tools, and maybe one of the hacks that starts in this week, will grow over the years into something that has significant impact for the community. But you never know. And for me, IPython was that, and it gave me a professional community and a scientific long-term effort. And hopefully some of what we do today will get there as well. So I think I'm going to hand it over to Yara now. I'll stop sharing so that Yara can actually dig a little bit more into what the specifics of IPython and Jupyter are.
All right, thank you. Can you hear me?
Yeah, we can hear you.
All right, so I'm just going to go over a very quick introduction to Jupyter Notebooks for the sake of time, and introduce you to some of the operations you could do inside the notebook, and then integrate and go from there, basically. So if you have all clones, the repository that Fernando mentioned, Intro to Jupyter, if you all open up the first notebook, that's Intro to Jupyter, you should see this notebook coming up. So basically, Jupyter Notebooks, it's a linear sequence of cells that you could run, in any order. And the three main cell types are code cells that are executable. You have Markdown cells for documentation, and raw cells. So this is an example of a code cell, and you can run it, and you can see the outputs, the result. And this would be a Markdown cell, and the raw cells are basically unrendered or unexecutable. This is an example of that. So one important concept is this is actually a modal interface, meaning that there's an edit mode where you can actually type into the cells, and there's a command mode, which means you're not editing the content of the cells, but you could do operations on the cells themselves on the notebook. So to know which mode you're on, basically, if you look at this screenshot, if you have this kind of outline around your cell and you see a cursor, that's when you're in edit mode. So if you press enter at any point in time, you go into edit mode, and if you press the escape button, you actually go into command mode. So if I click on this right now, you see I'm in edit mode. There's this outline here, and I could type. If I press the escape button, you see the background turns gray, and now I can't type anymore, but I can do operations to the cells themselves that I'll talk about in a second. So, I could just run the cell. Everything that I'm gonna show you, you could do with the mouse, and also there's shortcuts in command mode. So just very quickly, just with the mouse navigation, you could select any cell you want by just clicking on it. You could run it using the run button up here. You could interrupt the kernel. If a cell is running and you want to stop it, you could restart it. Copying, pasting, and also there's everything. The drop-down menus. You could cut cells, copy cells. You could go to the run specific cells that you want to run, or run all the cells, and manipulate the kernel. But what's nice is that because of the modality, the two different modes, you could also go into command mode and do a lot of these operations with shortcuts from the keyboard. So first of all, make sure you're not in command mode when you're trying to type into a cell, because then you're going to do operations that you don't want to do. You could, delete a cell by accident. So I'm not going to, show examples of all of these just for the sake of time, but you have the notebook for your reference that you could go through. But when you're in command mode, so basically, if I'm in the cell, I press enter, I go into edit mode. Now let me go back, and while I'm in command mode, if I want to move to a different cell, I could press the K or J buttons. So you can see I'm jumping around. You could also use the up and down arrows. You could actually change the type of the cell itself. So on this cell, if I do, if I use the M button, you see it's Markdown. If I do Y, it's code. So it's super handy. If I do shift enter, it actually renders it for you. And shift enter again here. Let's run some of these and discuss some of the things that happen. So if I just run a Python cell, it just runs it. There's no output because I'm not printing anything. If I print it, you see that it shows you the output here. But let's see what happens if I don't print it, but I simply do an operation without assigning it to a variable. So now you see if I do a plus 1, it shows me the output, and it actually labels it as the output corresponding to this line 5, whereas here there was no label. And similarly, if I run this guy, 6. Now, if I do this, b is equal to the underscore. That's a shortcut that's saved. Basically, every output is saved. So 1 underscore corresponds to the previous output that I had. So if I run this guy, and then if I output b, you see that it's equal to 12. If I do 2 underscores, it goes 2 back, 3 underscores, it goes back 3 times. I could even specify the actual number. So if I want to retrieve output 5 right here, I could simply do, just type it in here, we could do underscore 5, and here we go. We get 11 as we expected. So it's super handy. And it's also good to know there's different ways of executing cells as well. So before I talked about shift enter to basically execute a cell and go to the cell underneath. You could do alt enter or max option enter for running a cell and actually making a new cell underneath. Or if you don't want to even go to the cell below, you could do control enter. For managing the IPython kernel, so looking at some of the documentation here again, you could interrupt a kernel as it's running using the I shortcut. So if I simply run this and then I interrupt it by clicking I twice, you see that it interrupts the kernel while the code is running and it pauses it there. So this is useful, if I want to stop the code that's not working. In case you do something that kills the kernel, it basically asks you to restart it. So by running this block, we're intentionally going to kill the kernel by doing a segmentation error. And once it dies, you could just restart it. And when it restarts, you basically clear the memory. So everything I did before, these are not in the memory anymore. You could also use a different standard output and error strings for Python. Specify that in Jupyter Notebook, and you can see how it outputs them. So this is just the standard output using the print option. You could also specify the standard error, and it shows that it shows the error output in this kind of red highlight. It's good to know that with Jupyter Notebooks, the output is dynamic and in sort of real time. So if I print this and have a little pause or sleep command here, you actually see them printing in real time. If you have a super big cell, so this is printing 50 numbers, it's easy to collapse it by clicking this guy, so it doesn't take over your whole notebook. And I also mentioned Markdown for documentation. So very, very briefly, just Markdown is a superset of HTML, and it's super useful for documentation. And again, just like executable code cells, you could use Shift Enter to render them. So if I just go into edit mode here, you could do italic text, bold text. You could make lists. And again, this notebook is there for your reference if you want to revisit this. You could make lines. So if I render this, you see what it looks like. You could do like a block code like this. You could add a link. It's very useful. I'm not going to go through all of these for the sake of time, but also there is GitHub flavored Markdown. So you could basically not just do one line of code, but we could do blocks of code using the triple backticks, and you could do tables, using this notation. And importantly, I want to emphasize, because it's a superset of HTML, we could actually use HTML. You could make HTML tables, for example. So if we run this little HTML table, it renders it for you. And just a few last remarks. You could actually render images and video from your, locally from wherever your Jupyter Notebook is. So by just going to the subdirectory and the file name, you can access that file. So you could use the HTML syntax to render an image, by just using the, for people that know HTML, you could just load an image, you could load a video, so it actually runs if you click it. Now, the fact that I can actually render these images and videos from my local directory means that this is acting like a server that's accessing the files on the computer. And so security is also something to keep in mind. I recommend always starting your Jupyter Notebook from not the root directory, but wherever it is that you want to, the Jupyter Notebook is and the files that you want to render. And when you start the notebook, it actually generates a token for you that you can log out and log back into the notebook. And lastly, it's super useful that I could actually use LaTeX math commands in Markdown. So using the $, you could do inline math equations. You could do blocks of equations using the $2 signs. You could even do more complex LaTeX structure. So like I could render the Lorentz equations using the line command. But it's important to keep in mind that you can't do everything in LaTeX, like formatting documents and whatnot. This is just limited to the math, rendering. But it's super useful for the Markdown section. And that's a very kind of big picture overview, but it gives you an idea of how to navigate this interface. And with that, I can pass it to Shane to talk about some stuff that goes beyond just Python. So I'll stop sharing. Yep.
Thanks, Yara. So my name is Shane. I'm at the Colorado School of Mines. Let me see here if I can't share my screen. And Yeah. So I'm going to go over this notebook, Notebook 2 Beyond Plain Python. So feel free to fire this up and follow along. The original content for this was done by Fernando Pérez for last year's Hackweek, and I've modified it a little bit to go ahead and update some additional things. So I think, as was mentioned before, hitting Shift Enter is the basic way that you can execute a cell. You can do other sorts of things, like Control Enter will keep the same cell. If you do Alt Enter, then it will actually go ahead and create a new cell when you do that. So let's see here. Getting help in the notebook, you have these commands where you can do a question mark either to get general help or also for a specific command. So if you go ahead and do it for, say, numpy linspace, it'll give you the signature for that command. You can also do 2 of these to get a little bit more information, where this will actually show you, if you look at the difference between this first case, this is giving you the signature in the doc string that includes the parameters. The second case, where you actually call the double question mark, shows you the same information, but it also will actually show you the code that defines that. So you can see the actual Python code that's getting called for that command. There are a couple of other things you can do. Wildcards are accepted, so you can actually go ahead and you can find places where you have, and there's the quick reference card, which I'm not going to go over, but you should take a look at some point. Tab completion is really useful. So if you type something in, say np for numpy dot, and then hit tab, it'll actually show you all of the functions that are inside of the numpy library. You can scroll through this so you can see what numpy has in terms of different functions. So this is really useful for actually exploring libraries, where you can go through and you can figure out, what is inside of numpy. So tab completion is something that you can also do for documentation. So if you go ahead and if you write a function, as soon as you type the first parens, then you can do Shift Tab, and we'll bring open this little scrollable window. This behavior is a little bit different in the Jupyter hub than it is in just a regular Jupyter notebook. So if you have a server that's running on your own machine, you can see that if you do this, a single tab will bring up the signature, 2 tabs will bring up a little scrollable bit, and 3 tabs will actually detach it into a different frame inside of your web browser, so you can have the split screen view where you have this documentation, and you can resize that to have it persistent and be there. That doesn't work in the Jupyter lab because you can see that we already have a couple frames here. So it's slightly different behavior there. I think that Yara kind of already went over some of these underscores and history bits, so I'll kind of just go ahead and skip through this. But basically, you're able to access the output and the input history by going ahead and referring to things like variables like out11. So I think that for this, I would need to change this to 10 because I've skipped a cell. So if we do this to 10, then I think that should work. So previous inputs are available. History is something that I want to talk a little bit about. So this is a cell magic history. This end flag is saying, give us values 1 through 5. So if you do this, this will basically tell you what the first 5 commands were for this session. So this is different than what you'd be able to do in plain Python. So if you open up Python, if you try and do a cell magic, if you try and say, history, then that will fail. One of the things that's a little bit useful is that the IPython interpreter is actually more than just the notebook environment. So it runs an underlying IPython kernel So let's say that you're like me and you have way too many tabs open and your web browser, Safari or Chrome, crashes, and you haven't hit the save button recently. So maybe you think that you've lost all of your work that you've been putting into that notebook. You can open up a terminal, and if you type in IPython and fire it up, it'll give you a text version that's the same bit. And if we actually do history, auto tab completion works here as well. If we do history-G, what it'll do is it'll actually show you your global history. And you can see here there's an 8/14. So this says that the 8th session, these are the 14 commands that you've run. You can go through and you can actually scroll up and you can see previous sessions. So you can see sort of what I was doing earlier today for like my first session. And so each one of those commands is numbered on the right-hand side of the slash by the command number, and on the left-hand side of the slash by the session. And you can also, if you just do plain history, then you can see that it will give me just the history for this particular session. So we only had 3 cells for this one. So you can also access the underlying operating system, the operating system. Like the standard way to call commands is that you prepend a bang or an exclamation point beforehand. So if we do print working directory, that'll show the directory on the Jupyter hub that we're in. For some of the most common shell commands, like ls and print working directory, these things will work without even prepending, just because they're common enough that people do them interactively. But for other commands, if we say, for example, give us disk usage, Python doesn't know what that is. But if we do exclamation point disk usage du, it'll pass it to the underlying operating system and go ahead and print out the disk usage for the current directory. So in general, best practice is for you to actually prepend this bang, even for cases where you're doing commands that don't require it, just so that it makes it explicit that that's not Python, that's not working. What's nice about this is you can scoop the return values from the output and assign them to variables. So if you actually take the output of ls, you can assign it to the variable files, and then you can use that as a way to actually start to get some of that data into your Python session without having to copy and paste it directly from the shell. And you're able to do the same thing in the other direction, where you can actually take this Python variable name files and you can assign it as a shell variable file. And then when you go ahead and echo it, we're actually taking the Python variable and passing it into the shell. And so you're able to do interesting things. Files is a list. There's a method that will convert to upper, and we're able to actually do things like indexing to the first entry of the files, converting it into uppercase, and then passing it to the shell. All this stuff also works in multi-line blocks as well. So you're able to actually write loops or write functions that incorporate underlying OS system calls that are inside of actual loops or shells. So as I mentioned earlier, there are a couple of Python magics. So magic is basically any time where you have a percent sign. A percent sign for a single percent will basically work on the line that you're on, whereas 2 percentage signs will work on the entire code block. So you can go ahead and you can call magic, and that will give you the documentation for all the different magic functions. This is quite long, so I'm just going to sort of leave it there, and you're welcome to take a look at it later. But you can see that there's quite a lot of different things that you can do in terms of asking who's on the system, designating things latex, designating things markdown, so on and so forth. So here's a example of a system of a magic that I use pretty commonly, the time it function. again, this is a single line, so it has to be on the same line. If you go ahead and if you run this, it will determine based off of the first run how many runs it should do, and we'll try and estimate what's a good number of runs. So this basically ran it, found out that it was operating in some, pretty reasonably fast, and decided that it would be able to do 10,000 loops. If this was, say, 10 seconds, it would probably have done, 3 loops or 7 loops. If I wanted to do this for a function, you have to do it with the 2% signs in order to get the whole block code. And like the shell commands, line magics also work inside of code blocks. But note that this time it is going to refer only to this line. It's not going to take into account these functions. So you are able to do things. You can execute bash code directly by designating this a bash cell with %bash. So here is another disk usage example where you can go through and you can look at the underlying file system. You can also write files. So if we do this, we can do write file.txt. This will go ahead and this will actually produce a file called test.txt, and it will contain everything that's below the first bit of the cell. And if we cap this, we can see that this is a test file. I'm not going to execute this line because it's also pretty long, but this will show you all the different magics that are available. Just as a quick note, a couple of people have mentioned Vim. I like Vim. I use VI. If we look at the test file that we wrote earlier, should be here somewhere. Did it not write it?
It's in your intro Jupyter folder.
Okay, gotcha. Thank you. So if we change into intro Jupyter, and if we Vim test, a couple of people have mentioned that the way that you get out of this is that you can type :Q exclamation point. Vim is a modal editor, so if you type something else by accident, if you type I or something, then you'll find out that you can't actually get out. So if you ever find yourself stuck, a useful trick is actually to hit escape a couple times in the upper left-hand corner of the ESC button. That'll switch it to the command mode. So if you find yourself stuck, if you type Q or something and then you if you forget to type colon first, if you type Q first, it'll drop you into this, and then you won't be able to get out. So hitting escape a couple times, and then we'll drop you back into the command line, into the command mode, so that you're able to actually get out. So plotting, one of the really nice things about the IPython notebook is it gives you a unified plotting system where you're able to plot figures directly inside instead of them having them show up as separate outputs. So the flag to do that is the inline flag. So Matplotlib inline will enable you to do plotting inside of the notebook. So we've got an example here where we'll just show a quick chirp, and it will go ahead and plot out this directly inside the notebook. You'll notice that when we did this, we had to do plt.plot because it separated out the namespace. If you want to be a little bit lazier, one option is that you can actually use the Pylab Magic. So the exact same thing as up here, Matplotlib inline. If you replace this with Pylab inline, it will automatically import all of the Matplotlib commands as well as all the numpy commands directly in, and you won't have to prepend anything. So if we look at imshow, which is a command, this won't work because we have, it's not defined. If we go ahead and if we do Pylab inline, it'll give us a warning about the fact that we've clobbered a bunch of variables or bringing them directly in, and then we don't have to prepend the imshow command, it's just directly there. The same thing with all the numpy commands for zeros or for anything else. So I'm going to go over a little bit of an example here for profiling code. This is a function from the scikit-learn library, optics. I'm going to import it in and basically create some random data, and then we're going to go ahead and profile it. So earlier we used timeit, and timeit's really useful in cases where you are trying to figure out how long it takes for a function to run. But sometimes you would like to have a little bit more introspection in terms of where in the function it's actually taking longer. So if we run prun on this fit function, this will profile the entire code. So it tells us at the top how long it took to run the function. But what it also tells us as you sort of go further down is it tells you where that time was spent. One of the things that you'll notice when you look at this is that the times add up to more than total time. And that's because it's breaking it down by a different method. So there's this top level function optics that took 2.8 seconds, but there are other functions inside there. For example, query radius, validation calls, and it'll tell you what the time was spent, for example, looking up distances or querying radiuses. You can see how long it took for it to validate the arrays to make sure that they were valid arrays that included finite numbers. It'll tell you how many times each one of the functions got called. It'll tell you the total time that was spent and the per call time, as well as the cumulative time. So this is a way for you to actually figure out if you've written some piece of code, where specifically in that code things are taking longer, so you can try and figure out a way how to make it go a little bit faster. So Python has a bit of a reputation as being a little slow, which is not totally fair, but for loops are not that fast in Python. They're usually pretty slow. The way that we usually get around this is that we write things in NumPy, which are vectorized, but sometimes you'll have a function that's not very simple to actually write in NumPy. So here's an example of a function where you're basically trying to find something inside of a for loop, and there's no way to do it in a vectorized way. So this is an example that will take a raster DEM and convert it to an unconvolved waveform as you would see from the original ICESat sensor. So this is ICESat-1, not ICESat-2, but it has these two nested for loops. And if we go ahead and if we time it, what you can see is that you actually, this function might run a little bit slower than you would like. This is 91 milliseconds. That's not a huge amount of time, but if you were, say, trying to run this on a database that had, a 250,000 entries or several million entries, it might take, 6 or 12 hours or more time. So there's a couple different ways that you can do optimization. Python is pretty popular, but it's way more complicated to explain. So I'm just going to do a quick example with Numba. So Numba has a function called JIT, which is just in time. So it's a just in time compiler that will basically optimize your for loops. And so you can take this JIT, wrap the function that you wrote before. So this is the function that I defined, waveform C. I basically say just in time compile this waveform C and give it a new function called wave Numba. And if I do that and then run timeit, what you'll see is that you get a whole bunch of debugging information, but basically at the bottom, what you get is you get 6 milliseconds of runtime per loop compared to your original one, which was 91. And because this is a just-in-time compiler, it's actually a little bit faster than that, because when it went to do this, it did the mean and standard deviation in the first run. It had to compile it. So I think if you run it again, then what you'll usually see is you'll actually see that it goes a little bit faster on the second time and drops even a little bit more. So this is a pretty cheap way to optimize your code. You can kind of see that we just took one line and we basically made it more than 10 times faster, more than an order of magnitude. And if you plot the function, you can see that you get a waveform that looks like an ICESat-1 waveform. One thing that's important is that when you do this, there's two things to note. First of all, you're only really going to get a big speed up if you have things that aren't already optimized. So here we have 2 for loops. If you have something that's written in NumPy code, that code is already optimized. So this is a short thing that does a NumPy vectorized code. If you look at the comparison, what you'll see is that things get sped up, but they don't get sped up quite as much. So here, I think the difference between this and this one is it's about twice as fast, which maybe isn't worth your time to actually go ahead and do that. So don't go ahead and necessarily do this on every single function that you write, but if you have something that's taking a little bit of time, a little bit more time than you would like, this is a quick way to do it. This JIT function will only work on functions. It won't work on classes. And the other thing to note is that when you do this, you should make sure that your Python function and your NUMA function actually evaluates the same value. So here, if you look at the 2 different arrays that you get out, you can see that they're identical. So we can go ahead and we can use this function. If you were to do the same thing with the optics call that I gave an example of earlier, it would make it faster, but it would no longer be a valid output because there's a loop that can't actually be parallelized correctly. So if you do this, take an extra step and try and make sure that you're actually getting the output that you expect. So one of the things that's really nice about the notebook is that you can also put in direct, you can copy and paste outputs directly that include these formatting blocks, and you can still actually go ahead and it will evaluate this as valid Python. And you can do even, as discussed earlier, with some of these variables that are IPython specific variables referring to the cell input and output. So let's see here. We'll talk just a little bit about some basic errors and basic debugging. When you have errors that will pop up, you get a traceback, and that traceback will tell you where the line in your code is that things have gone wrong. And oftentimes, the way that it's done is it's done in a stack. So we called mod G. Mod G was what errored, but it didn't error directly in this. It errored inside of the function above it, which was this function G of Y. And then this function did not actually produce an error. If you look at this, it was taking a input of Y, which was 0, Y plus 0 plus 1 is 1. Where it actually errored was in the function above that, the F. So the last, when you get a traceback, sometimes these can be really, really, really long. Sometimes you know, and you're trying to figure out what happened. You want to scroll down all the way to the last error. The last error is the error where the error was actually propagated. Everything else that's happened is just basically been propagated up the stack. So you're looking at specifically this line here where this arrow is, line 3. This is where your error is, even though it's calling an error inside of this function and inside of this function because the error is propagating up. You can do debugging inside of the IPython notebook. There's a lot more detail on this than we necessarily have time to go, but if you call debug, you basically get this IPython debugger shell that it'll drop you into. And this shell, this is the interactive version of the Python debugger. There are a couple of useful commands that you can do on this. You can do things like you can run, let's see here. I think that what we want to do is we actually want to copy this and run it through. So I think that one of the things that happens in the debugger runs is that you actually, if you execute the cell below it, you lose control of it, and you're no longer able to access the, you're no longer able to actually access the debugger itself. So one solution for that is that you can just restart the kernel when that happens. But if we were to go up a little bit and then do this guy, so we'll go ahead and define that, and then we'll run this. If we run the debugger again, now what we're able to do is we're able to, if we run dir, this will give us some of the functions in there. You can call specific variables. So if you want to know what, I think that what we want to do is we actually want to run this guy. Okay, so we've run this, we've started a debug cell, we've run something in it, we're getting this division by 0. If we want, you can actually go ahead, if you run X, or if you run, you can run U, and that'll actually take you up the stack. So you can see where things are actually happening. So going U is up, doing D is down, so you can go up and down the stack to see where things are happening. I guess just the last quick point is that you can also run code in other languages. So for example, Perl will work. You're able to do other things in terms of, okay, you have to quit out of the debugger in order to actually get out. You can run different code in terms of running different languages. You can do code. You can also do C code or Python. But in order to do that, you have to actually have those languages installed. So if you wanted to run something from Ruby or something from C++, it would assume that you actually had Ruby installed or had C++ installed. I think with that, I'm going to go ahead and turn it over to Fernando to talk about interactive widgets.
Thank you, Shane. Much appreciated. I wanted to just make a quick comment. Let me share my screen. Let's see where my controls share. This is the guy. There we go. Yeah. So I wanted to kind of clarify one point of one of the issues that that Shane had right there about having to quit the debugger. It's worth explaining briefly what's going on. And what's happening is the debugger is a tool that Python runs that expects you to type information into it. But that process is not in the web browser. It's somewhere elsewhere on that server. So we basically have to connect the web browser all the way down to making that other process think that it is in a terminal where you would be typing normally. And that can be illustrated with a much simpler example using the Python input function that asks something. Are you enjoying this tutorial? No, Fernando is terrible. Okay, I haven't hit enter. And if you see at the top right here, this dot is filled out. That's an indication that the kernel is right now busy. If I hover over it, it says the kernel is busy, meaning the Python process is busy doing something. In this case, it's not computing anything. It's waiting for me to finish typing. And we can see that in that if I type here 1 + 2 and I hit Shift Enter, this cell gets an asterisk as if it was being computed, but nothing is happening. And obviously 1 + 2 should come back instantly. The reason is that the kernel basically, as far as it's concerned, it's not done computing this. So now when I hit Enter here, this cell finishes executing. It prints what I typed. And then this cell also completed because it was in the queue. But when you are in the debugger, you need to finish that process by typing Q. So when I type debug here, you see the kernel goes busy immediately. And as long as I'm in this debugger up, as Shane was showing, going down in the stack, listing my code, computing expressions, one very handy thing of this debugger is to help you say, well, I wonder what is X. So in this case, if you type an exclamation, the rest of the expression is evaluated not as a command, but just evaluated. So I wonder what X - 1 is. Oh, that's my problem. Because x is just 1, but x minus 1 is 0, that may be what's happening to me. This obviously is a toy example, but being able to dig into where an error happened, move up and down the function call stack, and compute pieces of expressions can be extremely handy if, for example, you're getting an error in a mathematical expression because one term is doing something unexpected or you have a mistake in it. Being able to do computations right there with the actual data. So you can type arbitrary Python here. I can type x plus 5 squared, and Python will evaluate that. So you can basically, it's a little microscope that you move around in your code to explore your data, but you have to remember, when you're done, you quit. And then you get control back of your kernel. And so what's happening here is you have to keep in mind that you have this web browser, but you have this other thing in the back that you're connected to, which is the thing actually doing the computation. So I wanted to just clarify that small point. And the other thing that I wanted to mention is that we're not going to get into that right now, but this notion of magics is available to you. There's a few built-in ones that Shane already illustrated and showed you how to get more information about them. But you can write your own magics, and the IPython documentation explains how to do that. So you can basically create your own pseudo commands. And as Shane indicated, you can make them operate on just on the content of the current line or on the content of the whole cell. These are the ones that have 2%. They're called cell magics. And basically, a magic is a function that takes the entire block of text and does whatever you want with it. In this case, it says, well, the Perl magic says this is not going to be Python code. It's meant to be Perl code. You can write a magic that executes in Fortran. You can write them when that one exists. There's magics for timing. You get to decide how do you extend the basic Python language with your own sort of personal utilities or domain-specific utilities and functions that can go beyond what the language syntax allows. So that's all I wanted to explain on that. Let's move over to widgets. So what we're going to do is I'm going to open this notebook, the 03 notebook. This notebook was written actually by Lindsey Heagy, our instructional lead who couldn't participate today. And I'm going to go briefly over it as an example, which is purely goal-oriented. This was an educational example of teaching introductory data science, geoscience students about linear modeling and linear regression from a very intuitive perspective using CO2 data from the Mauna Loa CO2 station to get them to think about what a linear fit does, what a linear model is, and how does that work with data which may have nonlinearities in it. So we're not going to get into the data. I just want to set up the context. I'm going to just run the code. There's some of the data for the first 5 years in the data set looks like. And we're going to discuss with students how to fit a straight line to these data. So how would I fit a straight line to this data? Here, we're going to write 2 small helper functions. And for now, I'm not going to go into the details of the syntax of how this works. What I want you to see is the end goal, the point that we're trying to illustrate is that we wrote a small function that fits a straight line. There's a slope and there's an intercept, and it plots the raw data and this line over the data. And here we write this function that we call widget fit CO2 that just calls this function to add a line and plots the data with our plotting function. So this is exactly the kind of thing that you would do as a scientist. But with this little block of code that takes this function widget fit CO2 data, and let me slightly increase my font size this way, that takes this function, which is just standard Python code, and calls IPython's widgets.interactive function and passes, you see these are the arguments to our function slope, intercept, minimum year, and maximum year. It passes those, and later we'll see what the syntax is. We get this object called W early year, and let's see what this object does. When we display this thing, this is what comes out. So what we now have is not just a plot of the data, but a plot of the data with the line superimposed, but a line that we can control and explore interactively. This is the slope of the fit. This is the intercept of the fit. So the idea here is to get the students to kind of play with the notion of errors and linear fits and whatnot and do an exercise. This kind of interactive exploration is very handy, but as scientists, most of us don't have the expertise and may not necessarily be interested in learning how to write complex graphical interfaces. The point of the Jupyter, what I call the Jupyter widgets machinery, which is the code we're using here, is to make it this simple for you to create these kinds of tools. If you want to explore something where it's more convenient to have a little bit of graphical control rather than typing numbers over and over and rerunning a cell 100 times because you actually want to explore, whether in this, as in this case, it's for educational purposes or just for your own exploration of some parameters in an algorithm or in a data set that you'd like to play with. With many traditional tools, that's the point where you would have to basically say, well, I need to either roll up my sleeves and go learn GUI programming or ask somebody in the team who is good at GUI programming. Jupyter widgets are not designed to let you write the next Photoshop, but they are designed to allow you to write easily small, lightweight, simple graphical interfaces, and not so simple, but it's certainly not an entire complex program like, say, Photoshop, that are tied to computational exploration. So if this was now an exercise, we'd ask the students to kind of imagine how would they predict with their choice of best fit that they eyeball with kind of the eyeball norm, and later on the exercise goes on discussing actual linear regression. How would they make a prediction? And what I want to show here is that even though these things are an output that you control interactively, you have access to those values. So the object W early year is a hierarchical object that contains these graphical controls, and you can actually get those values. So for example, we can say here, with this choice of slope and intercept, my prediction for 2030 is 393 parts per million. If I change my slope a little bit, maybe make it a little bit more like this, and I think that that's a better fit, let's see what happens. I can rerun, I can get those values again and repeat my prediction, and now I get a new value. So the point is, even though these are graphical controls mostly meant for kind of exploring output, you actually can connect them to a computational loop because you have access to their data. So the point of this example was to give you a high-level motivation for why these things can be handy and can be useful. Now we're going to dig a little bit into how they are built. So we're going to open the 04 notebook, and we're going to play with that one step by step. And I encourage you to play a little bit more with that 03 notebook, because it is a very simple but very nice educational illustration of linear models that is kind of relevant in our field, and it makes very good usage of these widgets for educational purposes. So this is what the actual code but they originated, first of all, when the project was called IPython only. And second, they are actually a Python library that you import. It turns out that because there are graphical controls in the browser, the project actually has two pieces. There's a piece in Python and a piece in JavaScript. And others have implemented the Python part in other programming languages so that you can get the same effect, but with the syntax that's appropriate, for example, for Julia. And so Julia has a version that uses our JavaScript communications machinery, but where the code that you run and import is actually a Julia package, and it works with Julia syntax. So we're going to run these imports, and in here, we're first going to discuss the high-level interface. There's a low-level API that I'm going to briefly mention at the very end, but there is a high-level interface, which is the one that I want to focus on right now, because honestly, for many common use cases, what we're going to cover in Notebook 04 is all you need. And the rest of the machinery is a little bit more low level. So the most simple entry point into the widgets machinery is called the interact function, which we imported right here. We imported a few things that seem related: interact, interactive, and interact manual, and we'll see what each one of those is. And this particular term, one called fix, whose use we'll see in a minute. So let's imagine that we have a function f, that all it does is returns its value tripled. And we'll see why I made it this way. So if I have this function and I call interact on it, So interact is itself a function. And I say, I want to interact with f, with x being 10. And I hit Shift-Enter. What happens is I automatically get a slider. And I get a slider that ranges from -10 to 30. And as I move that slider, the values, you can see my busy kernel little icon blinking up here. The reason it's blinking is because actually every time as I move my mouse, as I drag it back and forth, every single movement of the mouse causes a re-execution of the function, and you can see the value. And you see that we didn't put a print statement or anything. Interact automatically forces the return value of the function to be displayed. This is to try to make it as simple as possible for you to basically say, I have a plot function right here, let me make it interactive with this one call, okay? Now, what happens if I call the same interact function, but instead of x equals 10, I say x equals true. So what I get is a checkbox, right? And here you're seeing some of Python's interesting behavior with Booleans, that when Booleans are multiplied by numbers, Booleans actually behave like the numbers 0 and 1. That's a bit of an oddity of the Python language, which is there for historical compatibility reasons. In the early versions of Python 1 and Python 2, true and false were just aliases for 0 and 1, for 1 and 0 respectively. Literally, they were just true was equal to 1 and false was equal to 0. There wasn't a separate object called a Boolean object. Over time, Python did evolve true Boolean objects. However, in order to avoid breaking existing code that might make those assumptions, they gave them the behavior of integers under integer operations. And so we get this little wonkiness that a function that multiplies its input by 3 produces 3 times true is 3, whereas 3 times false is 0. But the point here is that as we call the same interact with first an integer and then a Boolean, we automatically get, in a sense, what seems like the right graphical control. You didn't, as a scientist, have to learn how to create a GUI for integers or how to create a checkbox or how to create a slider. You just call the thing you want to explore with the data that you want, and you get something sensible. This is what happens if we type a string. Hi there. Hello. Hack. And I'm typing deliberately slowly, so you see that every keystroke is being, so the function is being re-executed on every keystroke. And Python's behavior for strings is that strings do multiply with integers, and multiplication is just concatenation that many times. So that's what we're seeing here. I type whatever string I want, and that string is repeated 3 times, but that happens on every keystroke, right? And we'll come back to that. Now, this is how you use interact with an existing function. A very common pattern is to actually define a function, and maybe a function that you don't even need to name. I often use this as a name, just an underscore, basically a throwaway. But basically, this is a way of saying I have a block of computation that I want to play with interactively. So you can define it as as an unnamed function, because what happens when you use Python, the interact function as a decorator, is that now, and this is the syntax for decorators. If any of you is not familiar with that, we don't have time to cover it right now. I encourage you to look that up in the Python documentation. But very briefly, a decorator is a function that is called right before the definition line. So it is used with the @ sign. That's a special Python syntax. It is placed right before the def line. And it is a function that modifies the behavior of the function that is being defined below it. In this case, what interact does is call that function interactively. So it actually takes the function that is being defined and immediately executes it, but it executes it under its graphical control. So this makes it easy if you have a block of code to say, oh, I want this block of code to be interactively, indent it 4 spaces, put a def on top, define your parameters, call interact on it, and you're done. And you get all of this automatic type recognition machinery that we were discussing. So if you have questions, please ask them on the channel. I hope that we're going at a good pace. We're kind of on track with our schedule right now. So what happens if you have a function, let's say a function of 2 arguments, for which one of them you don't want a control for? You just want it to have a value. That's where this fixed thing comes in. That's why we import it. Let's say we have a function of 2 arguments, p and q. In this case, it just returns the pair, but I only want to play with p. And this is very common. You have a function that has a bunch of parameters, but you want to explore only one of them, those, you know, the values for the other, rather than forcing you to redefine it or give within the function itself default values. And you may be using an existing function from a library, and you just want to explore what does this particular model fitting tool do. For example, if I wiggle this parameter, calling fixed tells the interact machinery, oh, that particular argument doesn't need a control. It just needs to be evaluated always with the same value. So important and handy. Now, the actual elements that we've been seeing, such as checkboxes and sliders, do exist in the library as individually controllable entities. So you can say, I want a slider that ranges between so and so, and that takes steps of so and so. And this is how you do it. The widgets library, and in fact, I'm going to hit tab completion here. You'll see that it has a lot of things in it. The widgets library has lots of things in it. Let's say, for example, what happens, this is int. Things that begin with in, there's an int text, there's an int slider, there's an int range slider. Things that begin with float, there's a float, progress bar, there's range sliders, etc., etc. So there's quite a bit of it. We'll point you to the documentation later on. The point is you can create these controls manually with more specific values. For example, if you want this thing to go between -100 and 300, but at that point you want steps of 10, and you want the initial value to be 128, this will do that. And so that will tell you, I want a slider between -100 and 100, but that jumps in steps of 10 and begins at this particular value of 128. Okay, so you do have very detailed control, and that is what we were using here. When we created this widget, we made it be a widget that had fixed the minimum and maximum values to focus on the data range that we were zooming in the first 5 years, and that for the slope and intercept had very specific windows of values between 0 and 5, with this for the slope, a slope between flat and no more than 5 with this particular step size starting at 2, and for the intercept, it actually made choices that were based on the data. So the intercepts were chosen based on the data so that they would be sensible, so that you would expose to your users something sensible. Okay, so this is a table of what the automatic abbreviations do. If you don't want to create things by hand like this, and you simply use a specific value, what the widgets library does is it looks at the data, it infers from the data, and makes some choices. And these are the choices it makes, and the documentation has more details on ranges and whatnot. But basically, true or false booleans, you get a checkbox. If you type a string, you get a text box. If you give an integer, either value or a pair of values or a triple of min, max, and step, you get an integer slider. If you pass a single value or a pair of values or a triple of values with at least a float, you get a float slider. If you want more control, such as specifying the initial value, you need to use the manual constructors. These abbreviations are fairly simple. They only cover the most common cases. So for example, if you pass a 2 tuple of integers, it uses the default step size, but now you do get, without having to specify in slider, you do get the limits that you want. If you pass a tuple with 3, you get the min, max, and the step size. And the same thing applies if you use the interact function. It's the exact same thing, the same syntax. Lists lead to drop-downs. So if you pass a list, you get a drop-down. And if you pass a dictionary, you get a drop-down, but where the value that the function will get is the value in the dictionary, not the key. So this allows you to very easily make menus that are either simple menus where you just want those strings and nothing else, or menus that actually label specific parameter choices that you want to give to your audience. So as you can see, with this very minimal syntax, you already have quite a few tools to make interfaces for your existing code that allow you to do a lot of exploration. Now, in addition to the interact function, we also give you the interactive function, which is very related, and this is what we used in this example right here. We use widgets.interactive. The difference is that interact calls immediately. As we saw above, it calls the code right away. It's meant to just give you the graphical exploration and nothing else. Whereas interactive produces an object that you can then use. So it doesn't like interact make the call. It just creates an object. And now that object is an object of type widgets interaction interactive. That is the object that has this hierarchical structure. It's stored under children. In this case, we made for this function of 2 arguments. We called it with a equals 10 and b equals 20. And what interactive did is it created 2 sliders, as we said, with as a description there the names of the variables and the values min and max that we discussed before. And it also has an output area. You can display it either with the display function. The display function is part of IPython. We import it for you. It's basically the moral equivalent of print, but for things that are not text. It tries to display complex things. Now, if all you want to do is display W in a cell by itself, and this is the last line of your cell, you can just call the object itself, and that's what display will do. But calling display explicitly lets you do that. For example, do this, right? So that you still get the displayed object after, and then you can print something else afterwards, right? So display, these objects now are objects that you can manipulate, from which you can extract their data and their outputs, right? As I drag this, that W, this value is available to me. If I change this, I get the new value. So by using interactive, you have the same exact syntax and behavior and type inference that you get with interact, and the same simplicity, but now you get an object that you can manipulate, that you can pass around like a variable from which you can extract things. The arguments that are passed into it are available to you as a dictionary. So in this case, A is 21 and B is 25. If I change B to 48 and I look at its arguments, I see that now B is 48. And the return value is also available to you as a result. So this is why this is such a handy companion to the interact function, because it maintains its simplicity, but it gives you pretty good programmatic control. So we already saw a little bit of this, so I'm not going to belabor it, but because we actually just illustrated a richer example in this case. But this, now that you've seen kind of the whole machinery, this is meant to really show you how little code you need. I mean, this is an example of making, again, a linear plot with a slope and intercept. In this case, very simple. This is the kind of function that you'll write every day in your research or your teaching. And this is how little code you need to write to both get an exploratory widget available to you and to get something over which you have programmatic control afterwards, as we just discussed. Right? Hopefully, this is the kind of tool that can be very, very handy for you, both as an individual researcher and if you want to share exploratory interactive versions of your data. One important point in this API that I want to flag out before we talk a little bit about the lower level details is the fact that sometimes the function you want to call takes time. We've made a slow function here that sleeps for a second. So in this case, it takes time artificially just by waiting. This is a way of mimicking the fact that you could have code that takes a while to run. Okay, and so as you saw above, as I was typing or as I was dragging the slider, my functions were getting called all the time as I was doing anything, either typing if it was a text box or dragging the slider. That could become a problem if we start queuing up function calls and every function call takes 5 minutes. Then all of a sudden, dragging a slider once will mean that you have to wait forever. We actually don't queue up all the executions. We prune that queue, but still, it is a problem. So interact has a cousin called interact manual. and Interact Manual is the same exact syntax and functionality as Interact, but it adds a button so that you can make all of your choices. And if you have 10 different sliders and controls, you can play with all of them. And then when you're done, you have to push the button. And then the function executes. So you make your choices, you push the button, and the function executes and gets the value. So it's a very simple way to have the same capabilities against code that is potentially computationally expensive and where you don't want that every time. You can get the same thing with interactive. There's no interactive manual for API reasons, but interactive instead, you can pass the second argument via dict that says manual equals true, and then you get the same exact behavior here, where now nothing happens until you click the run interact. Okay. Now, if you're building your own widgets with your own elements, how do you get that? How do you get similar behavior, but just for a particular widget? Because there is a bit of an intermediate point where you may say, I don't want calls every time that there's any action on it, but I do want a call to happen, for example, when the user releases the mouse. For that, you can use the continuous update equals false flag on the constructor for your widget. So this is a slider that does get called. There's no run button, but it only gets called. If you see I'm sliding and sliding, nothing is happening. And the moment I release, okay, now it sleeps and makes the function call. The moment I release, it makes the function call. So this notebook gives you what I suspect is probably going to be somewhere between 95 and 100% of what most of you will need to know about widgets for quite a while, okay? The next notebook has a little bit more about how to build and play with these values and how to actually connect them into objects. And ultimately, what Interact produces are boxes. So we already saw this, right? And we already saw how to create a slider. This is now, we're looking at a little bit more of the API. This is, for example, how you can actually make a slider that has a specific label to it. And in this case, you can even include mathematics. In it. This is, as we saw before, the value. This will show you that there is actually bidirectional communication with your widgets. If I assign to the value, just watch what's going to happen upstairs. So I'm going to hit Shift-Enter now, and you see that value changed. Now I can move it down here, and then 8.5, Shift-Enter. So there is actually a connection between the code and the graphical interface. The connection is bidirectional. You can set up what are called observers, right? So this is a and here we've set up a variable that is the variable square, right, which is the slider value twice. And as I modify this value, square actually changes, right? The value of this standalone variable is now connected to this control. So you can actually build pretty sophisticated things. And the Vbox object is the object that allows you to construct layouts. And we don't have too much time to, well, basically no time to go into the details. This is kind of the more advanced, what would come next after this. But I do want to remind you something that I believe was already mentioned earlier on, which is the question mark in IPython. If you want to know about an object, you can type question mark, and we try to give you information about it. It shows you what the code is, what the signature is, what the doc string for the function or class is. And if you type 2 question marks, you get even more details that includes the source code if you can find it. So this is a very handy way of quickly learning about an object. And now I do want to mention something that I highlighted very briefly when I showed screenshots of the interface, but now I want to show you why that thing was handy. This idea of having a console, a scratch space attached to something. Let's say that I'm doing this and I want to learn a little bit more about the Vbox, but I don't want to have to keep cleaning my notebook because I'm just exploring it. If I say, give me a new console for a notebook, I get this thing at the bottom, okay? And let me show you let me type some code into it. Look at the prompt number. I was up here, I had been running code, and I had cells that had gone up to 16. This is cell 17. This thing below is like a terminal, but it is connected to the same data up here. So down here, I can type, for example, Vbox ? And read the same information without polluting my notebook, but on the same data. So I can see, for example, square here. And I get that value. Everything works the same, but there's no document here. This is just computational scratch space connected to the same data, to the same, fundamentally the same kernel. And so by using these two things combined, you have a document environment where you can do work that includes graphics, that includes graphical controls, and you also have access to the computational pieces of it sort of as you're exploring what you're doing so that your document stays as clean as possible. And combining these two things hopefully gives you a useful and productive environment. There's links in here to further things that you can learn and more sophisticated tools that have been built with widgets, and there's a lot more information. We've only scratched the surface, and I encourage you to take a look at the documentations on the widgets. But I believe for the purposes of this, the work of the next couple of weeks, this should get you on the right road, and we're happy to help you with questions you might have. I'm going to use the remaining 2 minutes to take a quick look at a few extra things connected to Python and IPython and Jupyter that you may find valuable. The first one is called Binder. If you haven't heard about Binder, Binder is a tool that lives at mybinder.org, is a project kind of led by folks in the Jupyter community that allows you to grab any GitHub repository, or actually any Git repository hosted on a variety of locations, and give users a new URL for it that is a live execution environment. So I want to show you, for example, that's what this button, Launch Binder, on this tutorial does. If I click on this button, it takes me to a URL of where that particular, oh, actually, we need to update that one and have the old version of this tutorial that Lindsey taught in Columbia a few months ago. And what's happening here is Binder is grabbing that Git repository, but cloning it and deploying a one-off little mini Jupyter hub like the one you're logged into. But the one you're logged into, you have an account, it lives forever. This one only starts ephemerally once. When I close it, it goes away, but it gives you the option of creating, let me show you, this is the Mauna Loa. Oh no, this one was an older version. This is the notebook. We need to fix that URL. But this is exactly the notebook that we were running, in this case being shown in the old Jupyter notebook interface. But if you see, this is exactly what we were just doing. But now it's living on some random cloud URL so that you can give this live executable version of your code to anyone who doesn't have to install anything. All they need is a web browser. They can run this on their phone if they want to. I mean, it's a little clunky to do this on a phone, but it works. And so Binder is a very, very useful tool within the Jupyter ecosystem for ephemeral reproducibility, basically. Very briefly, let me go back here. If you want to see really sophisticated Jupyter widgets, and I'm going to run over by about a minute, but no more than that. If you want to see really lovely, sophisticated uses of widgets for geoscience education, this particular website, Geosci Labs, which is a sub-project of the geosci.xyz project that Lindsey co-leads with her colleagues sorry, I want to go to the top level URL, geosci.xyz, which is geophysical resources in Python for education. This project, this particular repository includes really nice examples of sophisticated educational uses of widgets in the context of geosciences problems. Dashboarding, Voila is a project led out of QuantStack, which is a startup in Paris. And what Voila does is it makes it very easy for you to take these widgets and actually expose them as a standalone web application. Basically, if you don't want just to get widgets in the notebook, but you actually want somebody to see basically a rich web app that has these widgets connected to your computations, but no other sort of notebook-style, computing-style machinery, Voila is kind of a one-stop shop to make that very straightforward. We don't have time to cover it, but at least I wanted to flag it because I could imagine actually outcomes of the work in the next couple of weeks to be Voila services that expose, for example, access and computations done on ICESat data, but that expose them as a web app for the general public. And finally, I want to flag Jupyter Book, which is another project from our team. This one is led by Chris Holgraff, one of the members of my team at Berkeley, and a community that makes it as easy as possible to grab a collection of Jupyter notebooks and make effectively textbook-like looking things out of it. With hopefully minimal effort, it allows you to combine restructured text, Markdown, and notebooks and create static websites that can be connected also to computation, but that have more of a book-style feeling. We use these extensively. Thinking.com. Some of you may have heard that Berkeley has a very popular data science course called Data 8 that has had huge impact for us and has grown very, very large. It's called Foundations of Data Science, and this is the textbook for Data 8. The textbook for Data 8 is created with one of these Jupyter books, and we use this extensively to basically make textbook versions of our computational collections on campus. I will post some examples of geoscience-oriented books built with Jupyter Book. I know of two folks, Ryan Abernathy, one of the leads in Pangeo, has one, and there's a fellow whose name escapes me right now in Albany, New York, who has one also around climate data built with it that you might be interested in seeing. So I'm going to stop here. I want to thank the rest of the instruction team and Lindsey, who created some of these materials, who couldn't make it. I hope this was useful. Obviously, I spent a lot of my time thinking about IPython and Jupyter, so I'm more than happy to answer further questions, but I don't want to run over by more than 3 minutes, which is what I've already done.